To get started, which of these are triangle congruence postulates? In other words, if triangles have three matching sides, does that guarantee that they're congruent? What about if they have two matching sides and a matching angle between those sides? And if you're not sure about any of these, click over here to review. Right, these are all the triangle congruence postulates. Angle down here only tells you when two triangles are similar to each other. Let's quickly review these postulates. If you have a triangle and you know all three of its side lengths, then that's side, side, side. And any other triangle with those matching sides must be congruent. If you know two sides and the angle between them, that's side, angle, side. Again, any triangle with matching side, angle, side must be congruent. And if you know two angles and the side in between, that's angle, side, angle. And any matching triangle must be congruent. Finally, going around the triangle, if you know an angle, then another angle, and then a side, that's angle, angle, side, which also guarantees that two triangles are congruent. Now for all these postulates, you know three parts of a triangle with at least one of them being a side. So there's one more postulate we might consider. What if, going around the triangle, you know a side, then another side, and then an angle? So that's side, side, angle. If you look closely, you can see that this is different from all the other cases over here. So if you know two triangles have matching side, side, angle, is that enough to guarantee they're congruent? Let's find out. Okay, let's see if matching side, side, angle guarantees that two triangles are congruent. So here we have a triangle with a side of length 3, a side of length 5, and an angle that measures 35 degrees. And over here is a triangle with matching side, side, angle. These two triangles are congruent. Now see if you can make a different triangle that still has matching side, side, angle, but that's not congruent to this triangle on the left. Once you find such a triangle, click the Submit button up here. Excellent work! So here's a different triangle that still has a side of length 3, then a side of length 5, and then an angle of 35 degrees. So if two triangles have matching side, side, angle, that is not enough to guarantee they're congruent. But sometimes it is. Let's dive a little deeper and see what's really going on. You'll sometimes hear side, side, angle, or SSA, called the ambiguous case. When something is ambiguous, it can have different meanings. Let's see an example. Suppose you know a triangle has an angle that measures 30 degrees, and the side next to the angle has length 10, and the next side has length 6. So we know side, side, angle for the triangle. How many different triangles can we draw with this side, side, angle? Well, we can keep this angle 30 degrees, this side length 10, and this side length 6, but we're free to rotate this side in any direction. Now to form a triangle, this vertex here needs to be down on this line somewhere to close up the triangle. It looks like there are two places we can get a triangle, over here and again over here. So if we call these vertices A, B, and C, how many unique triangles have this side, side, angle? Exactly. If we rotate this side, we get one triangle, which we can highlight in yellow, but if we move vertex C over here, we get a second triangle that still has side, side, angle of length 6, length 10, and 30 degrees. So for this side, side, angle, we can have two different triangles, this one and this one. And that's why SSA is known as the ambiguous case. It's not clear which triangle you mean when you know side, side, angle. Now what happens if this side over here is a little shorter? Let's say it has length 5. Again, we can rotate this side around to see what triangles we can make with this side, side, angle. And the only place this vertex touches the line at the bottom is at this point over here. So now for side, side, angle of length 5, length 10, and 30 degrees, how many unique triangles are there? Exactly, there's only one possible triangle with this side, side, angle, and it happens to be a right triangle, which is pretty neat. Now what if we make this side over here even shorter? Suppose it has a length of 2. If we rotate this side around, it never even touches the line down here. So how many different triangles can you draw with side-side angle of length 2, length 10, and 30 degrees? Precisely, there are no triangles with this side-side angle. It's impossible to even draw one. Finally, let's make this side really long, even longer than the side over here. Let's make it have length 12. If we rotate it around, you can see that it definitely hits the line down here. So how many different triangles have this side-side angle, length 12, length 10, and 30 degrees? Excellent! So if we rotate this side a little bit, we have a triangle. But what if we rotate this side all the way over here? It still touches this line, but instead of a 30-degree angle, we now have a 150-degree angle. So this triangle does not match the conditions up here. And so for this side-side angle, there's exactly one triangle you can make. In general, you always get exactly one triangle for side-side angle whenever this side, the one that's opposite from the angle, is longer than this side, the one that's next to the angle. This is known as the SSA postulate, where the first S is a big S and the second S is a little s. So you can use this postulate whenever you go around the triangle and you have a longer side, that's why there's a big S over here, then a shorter side, that's why there's a little s in the middle, and then an angle. So depending on the lengths of the two sides, you might have 0, 1, or 2 different triangles that are possible. Okay, so let's try a few sample problems. Suppose you have two triangles, ABC and DEF. Here are a few different possible conditions that you might have. For example, over here, this says angle A has the same measure as angle D, angle B has the same measure as angle E, and side AB has the same length as DE. Which of these conditions guarantee that triangle ABC is congruent to triangle DEF? This is a tricky question, so if you get stuck, click down here. Nicely done. Let's quickly go through these together using sketches of triangles ABC and DEF. Let's start over here. Angle A is over here, angle B is over here, and AB is the side between them. If these are congruent to angle D, angle E, and side DE, then these triangles have matching angle, side, angle, or ASA. So these conditions here guarantee that triangles ABC and DEF are congruent. Next, let's look at these conditions. Angle A is here, side AB is here, and side BC is over here. So if they match angle D, side DE, and side EF, then going around the triangle we have side, side, angle. Aha! This is the ambiguous case. So these conditions do not guarantee that triangles ABC and DEF are congruent. For example, we could draw DEF like this. The angle and sides still match, but these two triangles are not congruent. Next, these conditions say that angles A, B, and C all match angles D, E, and F. This is a case of angle, 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 or AA. So in this case, the triangles don't have to be congruent, they're just similar. So triangle DEF can be bigger or smaller than triangle ABC, and they'll still have matching angles. And finally, over here, we have angle A, side AB, and side AC. If those are congruent to angle D, side DE, and side DF, then we have side angle side, or SAS. Triangles with matching side angle side are always congruent. So as you correctly found, these conditions guarantee congruent triangles. Let's look at one last example using the SSA postulate. Remember, you can use this when you go around the triangle and have a longer side, a shorter side, and then the angle. So which of these conditions satisfy the SSA postulate and guarantee that triangle ABC is congruent to triangle DEF? Think carefully about this third choice over here, where two of the sides in each triangle have the same length. Wow, great job! Again, let's quickly go through each case. First, we have angle A measuring 50 degrees, side AB has length 6, and side BC has length 4. And let's draw a sketch for triangle DEF. So going around the triangle, we have the shorter side, then the longer side, and then the angle. So that's no good. We wanted the shorter side to be the one next to the angle. Sure enough, here's another triangle you can draw with these conditions over here. So that's what can happen when the shorter side is opposite from the angle. You get ambiguous conditions, so triangles ABC and DEF are not necessarily congruent. Next, let's look over here. Angle A is again 50 degrees, and now side AB has a length 4 and side BC has length 6. And let's sketch triangle DEF. Going around the triangle again, we now have the longer side, then the shorter side, and then the angle. So this one works. Triangles ABC and DEF are definitely congruent by the SSA postulate. Now this last one was tricky. Angle A is 50 degrees again, side AB has length 5, and side BC also has length 5. And let's sketch triangle DEF. Going around the triangle, we still have side-side angle, but these two sides have equal lengths. We don't have a longer side or a shorter side. So are triangles ABC and DEF definitely congruent? Well, the only other way to have these conditions would be to rotate side EF so it's over here. So now point F is in the exact same spot as point D. This isn't even a triangle at all, it's just a line segment. And what's the measure of angle D over here? It's not even defined, since point F is right on top of point D. So triangles ABC and DEF are also definitely congruent for this case as well. It turns out that the SSA postulate works when the longer side is opposite from the angle, but it also works when these two sides have the exact same length. This was a really tough lesson, so congratulations for making it all the way through. Well done!